Imagine a medical scan so clear it could spot the absolute tiniest sign of disease. But at the same time, it's so safe it carries almost no risk. For a long time, that's been the holy grail of medical imaging. And today, we're going to dive into how a really revolutionary mathematical approach is getting us closer than ever before.
So here's the big question, right? How do we solve this puzzle? How can we get the best of both worlds? That perfectly sharp, life-saving image that doctors need to see without exposing patients to what could be harmful levels of radiation. It's this trade-off between clarity and safety, and honestly, it has stumped scientists for years.
Okay, so let's break this down. On one side, you've got your high-dose CT scans. The images, they're beautiful, they're crystal clear, but the radiation exposure is a real concern. Then, on the other side, you have the low-dose scans. They're much safer for the patient, but the image is, well, it's a mess. It's full of static and interference. We call this noise. And trying to find something tiny and important in there is like looking for a needle in a haystack, except the haystack is made of TV static.
So, to get around this problem, scientists realized they had to completely change their perspective. They had to stop thinking about a scan as just a flat 2D picture and start seeing it for what it truly is, a three-dimensional block of data. And that's where our journey really begins, by thinking inside the cube.
Here's how it works. Instead of trying to clean up the entire 3D image all at once, which is incredibly difficult, a smart algorithm breaks it down. It chops the whole thing up into thousands of tiny little 3D cubes, and they overlap. Think of it like a sliding window that moves methodically across the entire scan, cube by cube, making sure that absolutely no detail, no matter how small, gets lost between the cracks.
Okay, so now we have all these tiny, noisy cubes of data. What's next? Well, this is where the real magic happens. To clean them up, we first have to teach the computer the language of the human body. We need to build it what you could call a dictionary for anatomy.
And that brings us to this incredible concept called an overcomplete dictionary. Now, don't think of it like a regular dictionary. It's more like a massive, exhaustive encyclopedia of the human body. It contains a fundamental pattern, or atom, for every possible shape, texture, and structure you could ever find inside a person. This gives it a ridiculously huge vocabulary to describe things with pinpoint precision.
And this quote just nails it. It really is like having this special dictionary where there isn't just one word for bone, but thousands of unique words for the specific curve of this rib, the intricate texture of that lung tissue, or the delicate branching of a tiny blood vessel.
So you might be wondering, where does the computer learn all these words? Well, it learns from us. We feed it countless high-quality, clean medical scans, and it studies them. It learns all the fundamental building blocks, the sharp edges, the textures, the curvatures that make up a healthy human body. It's almost like a medical student studying anatomy charts, but just on a massive, super-fast digital scale.
All right, the dictionary is built, the computer has its anatomy textbook, now we can get to the real work, cleaning up those noisy cubes. This next part is all about learning the language of denoising. Now, I know this looks like some scary math equation, but trust me, it's way simpler than it looks. Think of it like a recipe. The noisy cube, that's Y, is the thing you want to make. The dictionary, that's D, is your cookbook full of every possible ingredient. And X, that's your recipe card, a super short list of which ingredients you need and how much of each to perfectly create the clean cube. And here's the secret sauce. It's a concept called sparsity. The whole goal of the algorithm is to be incredibly efficient. It's like a master artist trying to create a masterpiece with the fewest possible brushstrokes. It searches through that massive dictionary to find the absolute minimum number of words needed to perfectly describe the noisy cube. It's not about using more data, it's about using the right data. And when I say efficient, I mean, it's kind of mind-blowing. Instead of using hundreds and hundreds of generic pixels to describe some complex anatomical shape, this method might find the perfect combination of just 3 atoms, or words, from our dictionary to rebuild it perfectly. That's a revolutionary way to handle medical data. Okay, I know what you're probably thinking. This is all very clever, but how does building a shape with fewer pieces actually get rid of all that static and noise? We've talked about efficiency, but what about clarity? And the answer is just beautiful in its simplicity. That noise, that random, grainy static from the low-dose scan, it's just gibberish. It doesn't look like a bone, it doesn't look like a blood vessel, it doesn't look like any of the clean, anatomical words that the computer has learned in its dictionary. And because the noise doesn't match anything in the dictionary, the algorithm just ignores it. It gets filtered out automatically. It's that simple.
So we've done it. We've taken every single one of those little cubes and cleaned them up using our dictionary.
Now for the grand finale, putting all the clean pieces back together to create that perfect image.
The process here is really methodical. First, every single cube gets its denoising treatment. Then, they're all stitched back together into their original positions, like a giant 3D quilt. And remember how all those cubes overlapped? Well, in every region where they overlap, the pixel values are averaged together.
And this final averaging step? It is absolutely crucial. Think of it like the final polish on a sculpture. It smooths out any tiny leftover errors and, most importantly, it completely gets rid of the seams or blocking artifacts between the cubes. What you're left with is one single, seamless, beautiful, high-resolution image.
So let's zoom out. What does all of this actually mean in the real world? We've gone from a fuzzy, risky, low-dose scan to a crystal-clear 3D model that's safe for the patient. The future of medical imaging isn't just coming, it's here, and it is clearer than ever before.
With this method, you're looking at 3 huge wins. First, just superior denoising. We can turn low-quality images into high-quality diagnostic tools. Second, it's amazing at preserving the sharp edges of organs and blood vessels, those tiny details that are absolutely vital for an accurate diagnosis. And finally, as a cool bonus, this whole process also compresses the data, making it way easier to store and share these massive medical files.
But at the end of the day, what does this really mean for you? It means you can get the medical scan you need with way less risk. It means your doctor can make a more confident, more accurate diagnosis because the picture is so much clearer. And ultimately, that all adds up to one thing: better outcomes for patients, for all of us.
Think about it. We're essentially teaching an AI to read the fundamental language of human anatomy. If we can do that, what's next? What other complex, noisy systems out there in our world, from financial markets to weather patterns, could we finally decode if we just build the right dictionary? The possibilities are just endless.